Rethinking serverless with Flame. A bunch of my friends from Fly.io and the Elixir community have been hitting me up about this, and I wanted to take a look because they're rethinking serverless from scratch in a very different way, and I'm curious what they're up to. Imagine you could auto-scale simply by wrapping any existing app code in a function and have that block of code run in a temporary copy of your app. The pursuit of elastic auto-scaling applications has taken us to silly places. Serverless and functions as a service had a couple of things going for it. Elastic scale is hard. It's even harder when you need to manage those pesky servers. It also promises pay what you use costs to avoid idle usage. It's all good, right? Well, the charade is over. You offload scaling concerns and the complexities of scaling just to end up needing more complexity. Additional queues, storage, and glue code to communicate back to our apps is just the starting point. Dev, test, and CI complexity balloons as fast as your costs. Oh, and you have to rewrite your app in proprietary JavaScript, even if it's already written in JavaScript. At the same time, the rest of us have elastically scaled by starting more web servers, or we've dumped on complexity with microservices. This doesn't make sense. Piling on more web servers to transcode more videos or serve up more ML tasks isn't what we want. And granular scaling shouldn't require slicing our apps into bespoke operational units with their own APIs and deployments to manage. Enough is enough. There's a better way to elastically scale applications. I've heard a lot of good things. I want to look more into this. Don't necessarily love the framing thus far. There's a lot of real stuff here. Like when you go serverless, things are more complex. I would argue that going to scale is inherently more complex. And a lot of the patterns necessary to do this with serverless are best practices for scaling as a whole. Like your database layer should be something that can be interfaced with an unknown number of servers without having lots of issues. And yes, you have to build a bridge for that. Having queuing systems is something that should work without adding a lot of issues. And yes, there's complexity there. But this idea of what if you can just scale by wrapping your code in a function and have that run in a temporary copy? Interesting. See some split brain potential here, but I'm curious how this is solved. Let's take a look. The Flame pattern. Here's what we really want. We don't want to manage those pesky servers. We already have this for our app deployments via fly deploy, git push Heroku, Kube, CDL, etc. We want on-demand, granular, elastic scale of specific parts of our app code. And we don't want to rewrite our application or write parts of it in proprietary runtimes. This is such a Cloudflare call out. It's actually kind of funny. Let's see how this goes. Imagine we could auto-scale simply by wrapping any existing code in a function and have that block of code run in a temporary copy of the app. Flame, fleeting Lambda application for modular app execution. I love the name and the abbreviation. Very clever. With Flame, you treat your entire application as a Lambda, where modular parts can be executed on short-lived infrastructure. No rewrites, no bespoke runtimes, no outrageous layers of complexity. Need to insert the results of an expensive operation to the database? PubSub broadcast the result of some expensive work? No problem. It's your whole app, so of course you can do it. Interesting. Very interesting. The Elixir Flame library implements the Flame pattern. It has a backend adapter for Fly, but you can use it on any cloud that gives you an API to spin up an instance with your app code running in it. We'll talk more about backends in a bit, as well as implementing Flame in other languages. First, let's watch a real-time thumbnail generation example to see Flame plus Elixir in action. So I don't have a good way to make sound work here. Oh, look at that. My own videos being recommended. Oh, my own live stream being recommended. We got 230 people watching. That's pretty cool. If you guys don't know, I record these live, so feel free to join us on Twitch or YouTube every Wednesday when I make these videos. In order for this code to continue running, in order to get what data it needs to render this thumbnail to generate it, it spits out a child process, so another instance of the app to go do that FFmpeg bit separately and gives us a process ID to that instance, which with Elixir, you can have process IDs that are in different computers. And as long as they're on the same network and are networked together, you have access to communicate things between them. So for Elixir, this type of thing makes a ton of sense. But I don't want to dig deep through that video when they have more basic examples here. Let's walk through something a little more basic. Imagine we have a function to transcode video to thumbnails in our Elixir app after they're uploaded. Totally not relatable. Who would ever need to do that? Unlike every project I've almost ever worked on that has video, which is a lot of things. It's a very, very painfully real use case. Generate thumbnails. Takes in a video, which has a video ID, an interval, and we do temp is path.join to the temp directory. We generate a UUID so that we know this path is unique and clean, and we make this directory. Now we have the arguments for the FFmpeg call. So this is, we're inputting the video URL. We are splitting by frames, if I recall, is what VF does. Yeah, we're setting a video frame rate for 1 over the intervals. This is how often we want to generate new frames. And then we have this syntax for actually outputting that frame data. So now we're going to get a bunch of PNGs. If we put like 60, then every 60 frames, we would save one as a PNG. And then we run this command with system.command FFmpeg with those args. We get the URLs for the images here. We put them in VidStore, some separate thing that I'm sure they've implemented to actually store these thumbnails somewhere on the web, and now we have the URLs for them, and then we insert those into whatever we want to use them for. Our generate thumbnails function accepts a video struct. We shell out to FFmpeg to take the video URL and generate. Then we insert the generated thumbnails into our database. That's what the repo call is. This works great locally, but the CPU-bound work like video transcoding can quickly bring our entire service to a halt in production. Instead of rewriting large swaths of our application to move this into microservices or some function as a service, we can simply wrap it in a Flame call. Funny enough, this is exactly what I used Elixir for when I was building it at Twitch. Not specifically for frame generation, but for orchestrating a bunch of random video assets via FFmpeg, transcoding those, and then piping the outputs to random places. This is very painfully relatable to me. I have been there too many times and written a lot of things to do this manually. But now with Flame, we have flame.call, myapp.ffmpeg runner. And this is a function that does all of the same stuff, but now this can run on a different server. So when we call generate thumbnails, it's no longer going to block on the server we're currently on. That's it. Flame call accepts the name of a runner pool and a function. It then finds or boots a new copy of our entire application and runs the function there. Any variables the function closes over, like video and interval, are passed along automatically. When the Flame runner boots up, it connects back to the parent node, receives the function to run, executes it, and then returns the result. Based on configuration, the booted runner either waits happily for more work before idling or extinguishes itself immediately. Let's visualize this. Okay, so step 1, we provision a new runner that has this info. Step 2, the new runner connects to the parent. So this is that second runtime that just spun up, going back and forming a connection with the place that it came from that told it to spin up. The parent sends the function for execution. So there's forward, back, forward. The first thing is the parent server starts a new server. That server connects to the original, say, hey, I'm ready to do stuff. And then that original server sends the function that needs to be executed. So it can spawn that function. And then once it's done, it returns the result and then shuts down. We changed no other code and issued our DB write with repo.insertAll, just like before, because we are running our entire application, database connections and all, except this fleeting application only runs that little function after startup and nothing else. Okay, here's where I have actual useful input. The biggest issue most people run into with serverless is database connections. That's the bottleneck with most database stuff in serverless, is most databases can't handle lots of things having connections to them at the same time. And when you combine that with the pain of cold starts, where you have to ship all this code over, start up a box, make the database connection, and then get to work, it can get pretty painful pretty quick. This pattern doesn't solve that problem at all. It actually makes it a little less likely you'll notice it when it happens, and might even make it a bit harder to debug. So this is my first, and to be clear, having my first red flag this late is huge. They're doing some really cool stuff here. This is terrifying. The number of people, including myself, that I have seen run into issues because they have too many connections to their database at once is very real. And you could quickly run into a position where you're swamping your database with connections that you weren't expecting. And if that's not something you're already planning for, you're gonna run into problems. So this doesn't solve one of the biggest serverless issues I see. It might even make it worse. It won't make it much worse, but you have to pool your databases still. You have to find a way to manage database connections yourself still. In practice, a Flame implementation would support, they literally mentioned that in the next sentence, that they're in practice, a Flame implementation should support a pool of runners for hot startup, scale to zero, and all of these things. Specifically, a pool for the database separately, really important for this. We actually have Chris McCord in chat, absolute legend, creator of Phoenix, also the guy running a lot of this over at Fly, one of the people who gets Elixir better than almost anyone in the world, and I'm really pumped that he's in chat. No pressure, Chris, but appreciate you immensely for being here and for everything you've done, and having you here as we go through this is huge. So thank you so much. Fantastic work on this. It's really cool seeing people challenge the DX around scale in this way. And it's for my Elixir brain is going crazy here. I'm loving this. So solving a problem versus removing the problem. Oh boy, that's a bold title. This is something we talked a lot about when we had Jose Valim on the show before. The idea of we have these problems that exist in our tools. We can build solutions on top of those problems to Band-Aid cover them. But can we go deep enough to remove the problem from the root? This is actually part of why I like serverless so much, because it takes the scale problem and removes the orchestration part of it. You just run a function when you need a function and it disappears when it's done. That's something I genuinely really loved about serverless. It felt like it removed a ton of problems, but it did introduce new complexities that we had to deal with. I'm curious how this will frame Flame as doing similar. Functions as a service solutions help you solve a problem. Flame removes the problem. I think that functions as a service are a trade-off, but they do remove a lot of problems. The functions as a service labyrinth of complexity defies reason, and it's unavoidable. Let's walk through the thumbnail use case to see how. We try to start with the simplest building block like the request response Lambda function URLs. The complexity hits immediately. We start writing custom encoders and decoders on both sides to handle streaming the thumbnails back to the app over HTTP. Phew, that's done. Wait, is our video transcoding or user uploads going to take longer than 15 minutes? Sorry, hard timeout. Yeah. Funny enough, video encoding is one of the big things I hate Lambda for. Absolutely hate Lambda for this use case because you never know if you're going to hit one of those timeouts. I historically have relied on either running my own infra or third-party transcoding as a service stuff, even through AWS itself. I think AWS has like 3 different transcoding services, largely because transcoding on Lambda sucks so hard. So it's a very, very good example they picked for this, because this is one of the best cases for this level of dynamic infrastructure. Yeah, as they're saying here, like, sorry, hard timeout. Now you have to split your video into chunks to stay within that timeout, which needs even more Lambdas. Now you're orchestrating Lambda workflows and relying on additional services like SQS and S3 to enable all of that. Yeah, not great. The way I would have done this is when you need those thumbnails to be generated, throw it in SQS so you have a queue of the work that needs to be done. And then whatever number of boxes you're comfortable spinning up with a hard cap, or maybe you just leave one really powerful box running, which is what I usually ended up doing with these cases. That just constantly plucking things off of SQS and going through them one at a time or n at a time, depending on how many servers you have. But I would pretty quickly try to get out of serverless and into a queuing system with some real infrastructure spun up to handle this. Obviously, that's nowhere near as easy as just wrapping the function in flame.call, or was it flame.call, like just wrapping your function in this to solve that problem. That's much better. All this function as a service is doing is adding layers of communication between your code and the parts you want to run elastically. Each layer has its own glue integration price to pay. Ultimately, handling this kind of use case looks something like this. Trigger the Lambda via HTTP, S3, or API gateway, write the bespoke Lambda to transcode, place it in the SQS, write the SQS consumer in our app, persist to DB. Yep. Not going to say this is great. This is a really, really compelling example of why a pattern like this makes sense. We pay the FOSS toll at every step. I think the bigger cost here isn't how much money each of these costs, it's how much time and like mental overhead it costs to orchestrate all of these things. My biggest concern here is like the mental overhead, both for building and maintaining this, but also for debugging it. When you do have a problem and you have this level of complexity, debugging things becomes impossible, and like reasonably replicating things locally in dev is miserable. Even just the developer experience potential of having a real meaningful comparison of your local dev experience and your production one, making those closer with these complex things is a huge win. Flame backends. On Fly.io infrastructure, the flame.fly backend can boot a copy of your application on a new machine and have it connect back to the parent for work within 3 seconds. To be fair, a 3-second cold start is rough, but a 3-second cold start is an alternative to all of these steps. If it's not also blocking other things, that sounds nice. By default, Flame ships with a local backend and Fly backend, but any host that provides an API to provision a server and run your app code can work as a Flame backend. Erlang and Elixir primitives are doing all the heavy lifting here. The entire Flame.fly backend is under 200 lines of code with docs. The library has a single dependency, request, which is just an HTTP client. Because Fly runs on our applications as a packaged up Docker image, we simply ask the Fly API to boot a new machine for us with the same image that our app is currently running. Also, thanks to Fly's infrastructure, we can guarantee that Flame runners are started in the same region as the parent. This optimizes latency and lets you ship whatever data back and forth between the parent and the runner without having to think about it. So I'm starting to have like a big framing piece click here where it's almost like, where in your application are you splitting things up for scale? When you're building with Next.js on Vercel, they actually look at the different routes that exist in your app in which JavaScript is necessary for each of those, and they create a minified set of your application code for each of those endpoints. It's almost like the serverless like build happens as a compiler step thing, where it creates all of the serverless endpoints needed and all of the bundles of JavaScript for those to have an optimal serverless experience as soon as possible. Whereas the Fly approach happens, it's almost like the runtime version, where instead of a compiler generating optimal bundles for all of these endpoints, the runtime clones your current endpoint when you need a new one. So your abstraction isn't at like a bundle or build level, your abstraction's at like an infra runtime level that wraps your whole app. This comes with costs. Like a 3-second cold start compared to a less than half-second cold start that you would see in something like a decently optimized Lambda. But there's a huge benefit of not having to worry about that abstraction in the first place. This might be a hot take, but I actually see a really compelling use case here using it with Lambda, where Lambda is my default for all the code that I can possibly run in it. But when we hit a function like the example here with this big ffmpeg call, maybe call this in a way that gets spun out into a Docker image that's like a proper server to run that part. And then that takes over the request from that point forward. That I could see being really compelling. And it's actually kind of similar. It's a different level of abstraction, but it's similar to a bit of what Vercel is doing with their edge stuff, where with partial pre-rendering, the edge gets the request. It responds with something that it ran somewhere else, usually like cached content, and then the rest gets kicked off to a node Lambda. I could see something similar here where you have like an edge that intercepts your request that the user's making. It responds to them with content and then kicks off using Flame some processing in the background that's running your same code from the same code base. It's just a Docker image of it instead. So you can just write the code in there, even though that code will never run on your Lambda. I see a lot of potential for that type of pattern here, and I'm excited to see what people do with this. Look at everything we're not doing. With functions as a service, just imagine how quickly the dev and testing story becomes fate worse than death. Yeah, just touch on this a bit. Debugging, developing, testing, and doing all of those types of things are miserable once you've built this multi-piece architecture, from queuing to asset transfers to like network request management and all the things in between. It gets rough fast. To run the app locally, we either need to add some huge dev depths to simulate the entire function as a service pipeline, or worse, connect up our dev and test environments directly to that function as a service provider. With Flame, your dev and test runners simply run on the local backend. Do you guys want to know how bad this is? When I was at Amazon, it was pretty common practice for everyone to work on a box that was running like Red Hat Enterprise Linux, that was like a desktop directly connected to the AWS network. I believe it was West 2. It might have been something else at the time, so that you could treat that box like a node on AWS and interface with all of the services on AWS as though it was a production environment. That's how we were able to build things on AWS so quickly. And this is encouraging you to ignore all of that in a way that is very, very compelling to me. Yeah. With Flame, your dev and test runners simply run on the local backend. Very exciting stuff. But remember, this is your app. Flame just controls where the modular parts of it run. In dev or test, those parts simply run on the existing runtime on your laptop or CI server. Using Elixir, we could even send a file across the remote Flame application thanks to its distributed, the Erlang VM and Beam just being how they are. Beam's dope and lets you send crazy things over the network. On line 2, we open a path to a parent node. So we're actually streaming the file from the parent node to the child node here. That's pretty cool. Flame stream, yep, all the code is the same otherwise, but we're starting the stream here and then passing it through. That's dope. That's Beam doing its thing. On line 2, we open a file on the parent node to the path. Then in the Flame child, we stream that file from the parent to the Flame server in only a couple lines of code. That's it. No setup of S3 or HTTP interfacing required. It's easy to miss everything we're not doing. This is a good sign. We don't need to write code outside of our app. We can reuse business logic, database setup, pub sub, and all of those things. We don't need to manage deployments of separate services or endpoints. We don't need to write results to S3 or SQS just to pick up values back in our app. And we can skip dev, test, and CI dependencies and the hell of getting those all to work together. Flame outside of Elixir. Obviously, like a lot of this stuff is hardcore Elixir brained. So I'm curious what they have to say about using it outside of that ecosystem. Elixir is fantastically well suited for the Flame model because we get so much for free, like process supervision, distributed messaging, and all the other greatness we get from Beam. That said, any language with reasonable concurrency primitives could take advantage of this pattern. For example, my teammate, Lubian, created a proof of concept example for breaking out functions in your JavaScript apps and running them inside a new Fly machine. Cool stuff. I don't have the time to check that out right now, but if you guys are interested, let me know in the comments. I'll check it out in the future. So the general flow for a JavaScript-based Flame call would be to move the modular execution to a new file, which is executed on a runner pool. Provided the arguments are JSON serializable, the general Flame flow is similar to what we've outlined here. Your application, your code, running on fleeting instances. Complete Flame library would need to handle the following concerns: elastic pool scale up and scale down, hot versus cold start with pools, remote runners monitoring to avoid orphaned resources, and how to monitor and keep deployments fresh. For the rest of this post, we'll see how the Elixir Flame library handles these concerns, as well as features uniquely suited to Elixir applications. But first, you might be wondering about your background job queues. I'm curious to see what they have to say about background jobs. Flame works great inside your background job processor, but you may have noticed some overlap. If your jobs library handles scaling the worker pool, what's Flame doing for you? There's a couple important distinctions here. First, we reach for these queues when we need durability guarantees. We often can turn knobs to have the queues scale to handle more jobs as load changes, but durable operations are separate from elastic execution. Conflating these concerns can send you down a similar path to Lambda complexity. Leaning on your worker queue purely for offloaded execution means writing all of the glue code to get the data into and out of the job and back to the caller or end user's device somehow. I like this separation here. Durability versus like external non-blocking execution. Queues are really important for reliability. When you want to handle something after an error, have logic around how often you retry it, those types of things. Like, what happens if there's an error here? What happens if you don't have the permission to make this temp directory, and when you try to write the file stream, it errors out? What happens next? That's not a question that is answered well here. I'm sure there are answers, and I'm sure they're really good, but background jobs and queues are built to build these types of resilience, but we shouldn't have to reach for those for everything, which is what I'm excited about with this part here. For example, if we want to guarantee we successfully generated thumbnails for a video after the user uploaded, then a job queue makes sense as the dispatch, commit, and retry mechanisms for this operation. The actual transcoding could be a Flame call inside of that job, so we decouple the ideas of durability and scaled execution. Interesting. So again, with this example, that would mean like the whole generate thumbnails function fails if this Flame call fails. But if our job queue is running this function, that's not that big of a deal. I like that. I think that's fair. On the other side, we have operations we don't need durability for. Take the screencast above, where the user hasn't yet saved their video, or a machine learning model execution where there's no need to waste resources churning a prompt if the user's already left the app. In those cases, it doesn't make sense to write a durable store to pick up a job for work that will go right into the ether. Yeah, that's fair. When you put something in a queue, there's no guarantee that killing the thing that put it in the queue is actually going to remove that thing from the queue. Balancing that all out's a fun challenge. And I like that this model makes the ownership better by default and lets you break out to things like a queue when you have a reason to. I tend to love tools that improve the default such that when you have a reason to leave it, it's obvious and easy to do, and I'm seeing a lot of that here. With the Elixir implementation of Flame, you define elastic pools of runners. This allows scale to zero behavior while also elastically scaling up Flame servers with max concurrency limits. For example, let's take a look at the start callback, which is the entry point of all Elixir applications. We can drop it in a Flame pool for video transcriptions and say we want to scale to zero, boot a max of 10, and support 5 concurrent FFmpeg operations. Cool. So here, this is, I guess, framework-defined infrastructure, but it's still just traditional Elixir code, where we're starting Flame parent, and then we define all of the potential children here. We set a Flame pool with this name, this min and max, this max concurrency level, and then when it should shut down after idle. It's cool that you just configure that in code, and it happens how it should. I do like that. Feels a little weird just being part of your start code, but I get it. And I think it's cool that that exists and that that works. We use the presence of a Flame parent to conditionally start our Phoenix web server when booting the app. There's no reason to start a web server if we aren't serving web traffic. Note that we leave other services like the database myapp.repo alone because we want to make use of those services inside of the Flame runners. That's one of the interesting pieces. We have to make sure things we want access to in these runners are exposed in some way, like myapp.repo here to make sure this is accessible, but we're not actually passing all the stuff that's necessary for running the web server because we're not necessarily running a web server in these children. In fact, we're almost certainly not. Elixir's supervised process approach to applications is uniquely great for turning these kinds of knobs. And that's been my experience with it too. When I was using much more Elixir in production at Twitch, these were the things we were playing with constantly and using gen servers and crazy Kubernetes configs to keep our processes spun up in logical ways. The more I think about having those configurations in the language itself, the more compelling it gets. And I'm actually increasingly excited about this. We also set our pool to idle down after 30 seconds of no caller operations. This keeps our runners hot for a short while before discarding them. We could also pass a min1 to always ensure at least one FFmpeg runner is hot and ready to work by the time our application is started. It's a good call. This significantly decreases the likelihood you hit a cold start. You'll still hit them if somebody else makes a request and this box is busy, but you now have the ability to spin things up as you need them. Process placement. In Elixir, stateful bits of our application are built around the process primitives, lightweight green threads with message mailboxes. I don't think the implementation details are as important for this video. This is like really cool stuff. If you're interested to see more of how this works, both so you can understand it, but also so you could potentially implement it in other languages, this blog post is incredible. But I want to make sure we're focused on the actual experience you have rather than how these parts work. Remote monitoring. All a transient infrastructure needs fail-safe mechanisms to avoid orphaning resources. If a parent spins up, that runner must take care of idling itself down when no work is present and handle fail-safe shutdowns if it can no longer contact the parent node. Likewise, we need to shut down runners when parents are rolled for new deployments, as we must guarantee we're running the same code across the cluster. There's a lot to monitor here. Yeah. Fortunately, Elixir has all the primitives thanks to the Erlang VM. Yep. I'm curious how we managed to figure this out in JavaScript, but obviously Erlang and Beam OP as hell for these types of things. We'll cover those implementations in a future deep dive. Cool. What's next? We're just getting started with the Elixir Flame library, but it's ready to try out now. In the future, look for more advanced pool growth techniques and deep dives into how the Elixir implementation works. You can also find Chris to chat about implementing the Flame patterns in your language of choice. Definitely give Chris a follow. Absolute legend, one of my personal software dev heroes, and the guy who built the framework I first used in production. So huge shout out to Chris. Thank you both for being here in chat to answer my dumb questions and for making something this cool and really challenging the norm, because I haven't seen anything quite like this before, and I'm excited to see how we approach and adapt around these patterns. What about you? How do you feel about this fundamental rejection of the way serverless has worked all of this time? If you want to hear more of why I do and don't like serverless, I'll pin a video in the corner there where I talk all about serverless, edge, and how I keep switching between them all the time. If you're not interested, there's a video below that YouTube seems to think you'll like. Appreciate y'all as always. Always happy to have an excuse to talk about Elixir, and I'll see you in the next one. Peace, nerds.